All right. Can everyone see my screen?
Yes.
Okay, great. And hopefully you're seeing the right thing. So this chapter is on regression and prediction. Something that I thought was interesting that they pointed out a couple times, I felt like, is that in statistics, when you learn about regression, it's kind of, you're learning regression with the goal of like explaining why you get certain outcomes with the variables. So you have a variable or multiple variables, and you're using regression to see if there's a correlation, and hopefully therefore can explain like your ACT score, has this relationship with your college exam scores, right? And so, but in data science, most of the time, I feel like is at least what was implied here, is that typically regression's being used as a prediction. And that data scientists typically come at regression from that lens, that, okay, this is what has happened historically, and now we have this model, and now we're going to be able to predict what's going to happen in the future, as long as it's kind of within the same variation of the data we have seen, right? And it does go into like that we got to be really careful to not extrapolate. The pandemic is a perfect example of this, is that it's very, very hard and pretty much impossible to make predictions of what was happening during the pandemic because we didn't have historical data on what happens during a pandemic. At least nothing relevant since the Spanish flu was, over a century ago. But
and all of our predictions that include 2020 and the training data are going to have problems in the future, presumably.
Yes. Yeah. Anyway, so those are the points that I thought were really interesting and stood out to me. So the regression equation in its very, very simplest form, with just one x. So you have your y, your outcome, and you have a y-intercept, and then a relationship to the variable x. And this is called all kinds of things. Y is the response, the dependent variable, y variable, target. I like to use outcome. It's just my personal preference. And for x, you have the independent variable, the x variable, feature, attribute, predictor. So all kinds of names for the same thing. Okay, so we can read this equation to mean that y equals b1 times x plus a constant b0, or do you guys call this b null when it's a 0?
B naught, maybe.
B naught? Okay, yeah, B naught.
I just have to giggle because I was like doing the same thing of, well, B0, B naught, like what's right to call it? I don't know what's right. but in my head, I think it's B naught by
B naught.
default.
Thank you. So here's an example of some data that we have, and even visualizing it with the scatter plot, it's maybe hard to tell what the trend is here. And this sample data is exposure to, what was it exposure to? It's especially cotton dust. So years of exposure to cotton dust to their lung capacity. It's this ps4ds. And then real quick, so R is really cool because it was designed to do just this. So we can use LM for linear, which is just a straight line, and assign it to model. And so it tells us right here what our intercept is and the relationship to exposure. So we can kind of interpret this as for every year of exposure, lung capacity decreases by -4.2. I'm not familiar with ps4ds, so I don't really know how drastic -4 is. I'm not sure, but it's negative, and decrease in lung capacity is bad. I think we can all agree. So, but you can also have these models to exclude a y-intercept, and we do that by just adding this -1. And then, as you can see, now it just has 20, which I don't think that's very good. At least if you want to look at the model to be able to like interpret like what's happening here.
I mean, in this case, excluding the intercept is saying the model has to go through 0, 0.
Yeah, right.
So like if you have no exposure, you have no lung capacity. It's kind of
Yeah.
like you're nailing the model down to saying that, which doesn't feel right.
No. It's probably it only makes sense when you have like a lot of variables, I would think. And yeah, I would just try to think through maybe the next example that would make more sense, right? The next example is housing prices. And you know, if you're using like the number of bathrooms and the number of bedrooms and the square feet and the size of the lot, right? If those are all 0, right, your property is 0 square feet and you have no rooms and you have no bathrooms, that would kind of make sense that the value would be 0 because you're not selling anything. So maybe in that situation that would make sense, but not for this example. It was just mentioning how you can do it in R, is take away that y-intercept so that it has to pass through 0.
And so is that why the result there of 20 is so different from -4? Because there was a sort of a negative trend, a slow negative trend when you include when you don't omit the y-intercept. So the first version, it's -4 and there's a little bit of a slow trend, but then you put the -1, force it all to go through 0, 0, and now it's doing its best to make the data, the trend to be positive now. And I guess that's,
yeah.
Does that make sense?
Yeah.
Yeah, because it's saying that if you have 0 exposure, you have 0 lung capacity.
Right.
And so since you forced it to think that, it's like, well, but some of these have lung capacity, so I guess it must be a positive correlation.
Right. And
yeah.
I think it's more the way that these the linear regression line is calculated is that it's trying to minimize the residuals as much as possible. So yeah, when you force it to pass through coordinate 0, 0, right, the way it's minimizing the residuals is trying to get up to this, you know, around 400 ps4ds as fast as possible, right, to get that line up there so that it's decreasing the residuals. And yeah, we're going to talk a little bit more about that. So yeah, so this is the original line that has the intercept up here. So the 424 plus -4 times the variable times the exposure. So you get up here. So you have your y-intercept right here, your b0, and then this slope down. And it's just showing that your coefficient for your exposure variable is that change in y divided by the change in x. So delta y over delta x. And it's negative. All right, and so now we're kind of talking about the residuals. So this is kind of the formula that explains the original data, right? So if you picked a point and you used our linear model that we just did up here. So that plugs in for B0 and B1. But then we have our exposure somewhere on here, like 10, and but in our original data, sorry, so if you pick a point, right, you got your exposure that lines up with that point and the outcome. And so if we plug in all of those values here, 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 and here, what you have left is this error, right? That takes us from that line, but then is able to move us up or down, whatever the case might be, to our original value that explains why. And so, yeah, when you're kind of going back to then apply the equation to try to fit the exact data points you had, there's this error here. And so the formula for the predicted values is now this y hat, right? So we have a predicted y hat, and the, oops, that's a typo. That's supposed to be a plus. Sorry about that. Plus there, not equals. So y hat equals the b0 hat plus the b1 hat times our exposure. And yeah, and then our residuals are just calculated by taking our original data point minus the predicted, because this y hat is going to land on that line, on that perfect straight line that we drew. And so yeah, this is.
I make sure I understand the hats here. So y and y hat, I think I get, like, you know, one's sort of the actual point and one's on the line. I know the book talked a bit about hats, but here we have also, like, in the top line, the EIs, the whatever you call that term, doesn't have a hat, and the B0 and B1 don't have hats. So is it correct to interpret this as, like, the top line here is some hypothetical reality where there's, you know, actual values of B0 and B1 that are somehow there, and then our model, all we can do is estimate B0 and B1, and that's why there's hats on those? Did you see where I'm?
Yeah, yeah. That's,
Yes.
that
Okay.
makes sense to me.
Yeah, that the unhatted is like the, always like the real value. The I mean, sometimes it's population, sometimes it's sample, or it's not sample. Sometimes hat means samples, but because it's not the real thing. It's the
Like
little
an
piece.
estimate, right?
Yeah,
It's like our guess, or whatever process we use to obtain that.
right. And so here they've got the hats because they are predictions, they're estimated values. It's funny, I have not worked in a science that uses hats. Like, it wasn't ever a thing that I remember in any courses that I had way back when. But some courses love their hats.
Yes.
We used them differently for something.
Okay.
Yeah.
It makes character encoding much more difficult. That's all I know about the hats. All right.
All right. Let's see. So this is just showing us how in R we can find our fitted values here and our residuals with R. And if you, if you plotted the residuals, right, you're going to have positive and negative, and it's kind of centered around 0, Y, and they're just going to be up and down, up and down, up and down. Because again, our linear line is trying to minimize those residuals as much as possible, which is, which means typically you have kind of, well, it averages out to 0, right, with your positive residuals, your negative residuals. All right. Trying to remember what I was doing here.
I have a question on the residuals, particularly like plotting them out. What would be like the value of a graph of the residuals? I guess that if it's all closer to the line of 0, then you know that there's a higher correlation, but you can also get that from the final statistic, right? The R squared. And I'm still recalling like a lot of this from many years ago. So if I'm not getting the words right, but I'm just wondering, like the value of graphing the residuals, what can you interpret from that?
So yeah, I think what you said, correlation, I feel like I would do that as just an exploratory thing for to make sure I'm understanding the data, but potentially an outlier is maybe something I could see from the residuals here.
That's true.
Here's the residuals. I mean, not exactly, but the red dotted lines are kind of showing you what the residuals or the error, right? What did I call that? Explicit error? But yeah, so like, perhaps not this data, but if I was seeing a lot clustered together on that 0 line, but then one really stood out, or it just kind of was and I would anticipate maybe a little like uneven, because outliers can really pull that influence the line when it shouldn't, because it's just one value, but because it's so far away, right? It's pulling that line up or down depending on where it is when it shouldn't. I don't know. That's what comes to mind when I think about what information can I get from looking at plotting the residuals. Does anyone have any other ideas?
So I have a question. Hi, this is Pavitra. So that QQ plot or something like that. So is it possible just to see residuals without having the predicted versus can we actually see those lines themselves as a distribution? Is that what that QQ plot or something like that does?
I don't know if it'd be QQ, but like if you didn't mean like a histogram on the residuals, something like that.
Well, I mean, I remember that R has the ability to generate like 4 sets of line graphs based on your residuals. And I'm wondering if I'm talking the same thing, but it's basically, it shows you how closely they are like concentrated, or if they are like just a little bit all over the place, because then that means that there could be a possible, there could be something there like which explains the model. Like, and I could just be completely speaking nonsense, but it seemed like it was called QQ plot. But yeah, but the other question I had was, is it possible to see these lines, like the residuals, like can we actually plot that in something just to see like the distribution of that?
I mean, we totally can. Like, you want me to try doing that now?
Well, no, I wonder if we have any inbuilt functions that enable us to do that, and if anyone was familiar with that.
I would think this, sorry, this is Stan, I have my video off. I would think this is a lot more informative actually, because you can see like, if you plot the predicted versus the residuals, you can see like where along the predicted values, the model starts to do a poor job at explaining the variability in the data. And yeah, when you were going over this, like I read the R for data science textbook a while ago, and that was one of my biggest takeaways from the modeling section, was like just plotting the residuals to evaluate the model fit, especially when dealing with nested models. I think there was one that was like looking at life expectancy in a bunch of different countries, and I forget what the metric was, but you could see that there were some using the same model for each different country, but running each country separately, where the model just did a really, really poor job at explaining the variability in the data. And that was just from looking at the residual plot.
So that was the Gapminder data set, and it's
yeah, there you go. Thanks, Ryan.
Yeah, it's in chapter 25 of that book. I was just looking at it because I remember there were some plots of the residuals that came up there. I'm trying to see what the code was that actually plots that. So once I see that, I'll mention it.
Thank you for your questions and the conversation. I wish I knew the answers, but I don't.
Yeah, don't worry when you don't know the answers. That's why it's a club.
All right. So all right, multiple linear regression. So this is the same thing, but now we have multiple variables to predict our output. So we have this data on house sales. And so we have the adjusted sale price, this square foot total of living space, the square foot of the lot, bathrooms. I'm confused a little bit about bathrooms. Is that just the space of the bathrooms? Not the number of bathrooms, I would think. That's funny. Number of bedrooms and building grade. Now I'm really curious about this bathrooms. I figured it would be
It's-
the number of bathrooms, but no, I'm really looking at it.
That's got to be square foot. That
Yeah.
seems large-ish.
There's zeros.
And there are zeros. Yeah. So the zeros are probably actually NAs.
Yeah, I wouldn't buy a house without a bathroom. I don't know about you guys.
I suspect, I don't know, but it almost looks like the columns are shifted over because like the
Ooh.
square foot living,
Yeah.
the square foot lot, like
Oh.
bathrooms 3 3/4 make sense as a bathroom.
Well, 21111 also makes fun
It does.
sense as a
yeah.
bathroom.
Oh, yes, yes, yes.
Bedrooms is the 3. I'll bet. Well, how do you have 3.75 bedrooms?
See, like I don't know, but yes, so, I don't know. That was
Yeah, that's funny.
How weird.
Okay.
Well, I was trying to use tidyverse instead of the
Yeah.
read.csv, so I probably
Oh,
screwed up.
you did read TSV.
Oh, yeah, because it's
Is it?
It is. But
Okay.
let me, you know what? Let me just rerun this. 'Cause it's gonna drive me crazy. And this is the beauty of our markdown.
Yes.
Let's replace the, if I can find it. Where are you? There it is. One second. It doesn't want to do it the way that the original did it.
Nope.
Parent file RT can open the connection.
Is there something wrong in the file name?
I don't think so. It looks right to me. All right, well, we're going to pretend there's not an issue and I'll fix it
Yeah.
next time. Okay.
So let's not draw too many conclusions about the true
Yes, yeah.
value of houses in King County, but the way that it's run is fine.
Yeah. Okay. So, oh yeah, that's gonna really mess us up. That's fine. Okay, so, but in theory, we want to figure out how square foot to living, the square foot of the lot, the number of bathrooms, number of bedrooms, and the building grade, their relationship to our output, which is the adjusted sale price. So yeah, don't look too closely at this, but have your intercept and then the coefficients to go with each variable. And then assessing the data. So if we just do summary on the model, tells us what we told it to do, right? As far as making the model. And now we have our residuals, right? We have our minimum, first quartile, medium, third quartile, and max for our residuals. And then our coefficients. So this is the coefficient that they're putting here, and then the standard error, the t-value, and the p-value, right? Pretty sure that's what that's supposed to be.
Yes.
We have degrees of freedom down here. Anyway, gives us gives us a lot of good information. So anyone have anything to add?
Well, I think so. I was trying to figure out what the columns really are, and so it's interesting. Like I think the one that's labeled square foot living is actually the square footage of the lot, and then it was.
It's not going to be. It's not going to be accurate though, because the adjusted sale price right here.
Isn't that like?
This is supposed to be the square foot to living, I think.
Oh, square foot to living. Yeah.
Because
or wait, total. No, it's not two. It's total. It's total, not two.
Yeah, total living space, I think.
So
is it sale price in millions or something?
I think the adjusted sales price is in millions or something like that. And that's why you're seeing 0.9.
Okay.
Yeah. So I think it is. I think that column is correct.
Okay. Whew, thank goodness.
But the square foot total living is the biggest number, and the square footage of the living space can't be larger than the lot size. So I think that's the lot size, and then I think that's probably
you have multiple stories.
I'm not sure what the 2111 column is. I think that the bathrooms column is actually the living square footage. Oh, you're right about multiple stories, Jonathan. Huh? But it's off by too much. Unless these are multi-family,
like 1 acre.
Well, so I don't know what building grade is on a scale of. I was thinking that might be building grade, and then because the bathrooms, like the bathrooms, is the only number that should have 0.75s and 0.5s. I would think. You can't have 3.75 bedrooms. That doesn't make sense to me. But you could have 4 bedrooms. And then
I think the building grade is like on a 6-point scale.
Anyway, it doesn't really matter because whatever feature A through feature E.
Yeah.
Or F. Feature A through feature F. So, but yeah, we can still look at like the different levels. Significance levels.
All right. I see. So this is, according to our intercepts, houses just start at what, 0.8 million or whatever the case might be.
Yeah. In this data set.
Yeah, right. All right. I'm happy to go back up, but okay, model selection and stepwise regression. So stepwise regression. So we could, with our data, technically we could use every single variable that we have access to make a model. But that's not a good idea because there's a lot of noise, and it actually points out that the noise doesn't hurt as much in linear regression because it's a straight line. But if you were doing a different kind of regression where you gave your model freedom to be more sine or cosine, right? That prediction for the noise becomes a way bigger issue if you're making it consider too many things, and then it's just going to cause problems. It's not going to. It seems like it seems more accurate to the historical data, but it's not going to be as accurate for your actual future variables that you're looking at. Okay, so stepwise regression is pretty much, there's two ways. You can stepwise forward, where it kind of adds one variable at a time, and sees, how well that's working for it. And then eventually it will stop once it's like, yeah, adding another variable is not going to be beneficial. And then there's backwards stepwise that starts with all of the variables and then just takes one off at a time until there's a pretty good fit. So direction both. Okay, so this one, so we're still working with our sales, our house sales. And this is step AIC, which is, I knew this, but now I have to look it up. There are too many pages to look through. Where did you go? Oh, there it is. So, oh, you could go ahead.
No, I was going to try to help rescue you, because it is a lot of pages, but was it a Kaike's information criteria? I don't think I've ever actually heard that pronounced out loud. The A.
A Kaike. So it was created by Hiro Tagu, a Kaike. And so, yeah, so a Kaike's information criteria is what that AIC stands for on page 157. So then there's all kinds of variations, but the one we're using in this example is a Kaike's information criteria. So this is direction both. So it's going forward and backwards to try to find the best model with the correct and right number of variables to consider. So I'm trying to figure out, is this increasing or decreasing? Start step. Did you step up or down? Down. Okay. So this is, so as you scroll down, it's slowly taking off variables. So I'm not familiar with this function. I've never seen it before. It's showing me, so what I'm interpreting is that it's showing me its steps that it took. So it started with all the variables, I think, maybe not. And then it's showing me taking off the worst one at a time. So it's step, step, step. Should I assume this last one is the one it's recommending?
I mean, the general idea here, right, is that adding more variables, predictor variables, should never make your model worse, technically, but it does make it more complicated. And isn't AIC kind of trying to balance, is the gain worth the additional complexity? And so I guess it reaches a point where I think this last one is probably, or is it the second? Like I don't know, but at some point it says, okay, all these variables are worth including in your model, and then then it's the that maximizes the AIC, or is it minimizes this? I don't know. Which way does that go?
Right. I think I remember now. So you're right. The more variables, the better your model. But in statistics, simplicity is like number one holy grail. But there's also the fact that there are variables that are like very related to each other. And when you're using both of them, it's their coefficient isn't an accurate explanation with its relationship to the output, because they're conflicting with each other because they're explaining the same thing. You want
I think that's a concept of multicollinearity, I believe.
I'm sorry, what did you say?
Multicollinearity. So that's one of the assumptions of regression, right? That we don't want to keep multiple collinear, basically highly correlated variables together. So you want to, like in the steps or in the process of when we are eliminating the variables, that's one of the things we want to take care of. And we remove the highly correlated or multicollinear variables.
That's right. Thank you. What direction is this number going? It is.
Is there like a summary function that you could just print on your step LM object that would give it to you maybe?
So here's step LM. So does this end up being the same thing? Your built, square foot, finished basement. Sorry, let me go. 1, 2, 3.
And I'm trying to remember, does the step function do like interaction terms as well, or is it just additive?
I don't know. This step LM has less variables than the last one in the AIC.
Okay, so I guess it makes sense that that's probably the last. I guess one thing, I didn't read this chapter yet, so this is kind of just like thinking generally about this, but like good stopping rules for like AIC, or when you deal with BIC, like you know, typically you would just choose like the lowest AIC or BIC. I don't know if they like talk about BIC, but it's basically AIC, but you get an additional penalty for the number of variables that you include, so it's a bit more stringent. But like at a certain point, you're just getting kind of marginally smaller, and like Jonathan talked about, you're increasing model complexity for maybe describing a little bit more variability. Like, does anybody have any thoughts on stopping rules, like after X amount of drop in AIC or BIC, we're going to call it? Or
Well, I know I don't.
also, if that made no sense, then I'll just stop talking.
No, thank you. It mentions BIC. It gets one little sentence in this book, but it mentions it.
I thought it was a great question, and I can't wait until I can answer it confidently.
Right.
Yeah, I think I mean I think this was more, or this may be more appropriate for like classification, where like I've done this in genetics, where you're like looking at how many clusters are there, and you can always try to whittle it down to more and more and more, but then eventually it starts to not really make sense, or not make sense, but your gains are pretty marginal. But maybe we can table that for now.
You're also a lot more likely to have problems with new data if you get
if you like
into
over
these-
cluster or
Right.
or over split.
Yeah, if you're using some variable that really doesn't have a relationship, but you tell the model it has to have a relationship, so it's going to find one, and it's going to be what is the relationship in this exact set of data. And
Right.
so that's something to really watch out for.
Yeah, you can't really generalize to new data.
Right.
And then I think this was just to show the difference between that just using the number of bedrooms to determine the sale price of the home is too not good on its own. Well, and it does make sense, but and the reason it makes sense is because if you're not increasing the size of the house with the number of bedrooms, the value of the home actually goes down when you just make smaller and smaller bedrooms to fit the same size of the house. No one wants small bedrooms. So that was just, go ahead.
Just that, but we don't know if that's what we're actually seeing
right
in this exact example.
Right. Anyway.
Yep.
Well, that was just a fun little thing to throw in there. And yes, if it's okay with everyone, I'm not going to go further into the chapter for today. And that's where
I was gonna say, I think that worked out perfect.
That's where we'll pick up. I'm so glad, because I felt really bad. I was like, I did not get very far.
And now we have a little break. Everyone can get caught up. So we're gonna take 2 weeks off. We'll be back on the 12th, I think it is. And we will continue with chapter. Yeah, it is the 12th. We'll continue with chapter 4. It's a thick chapter. There's a lot going on, obviously, since we made it about, halfway through ish in an hour. So,
John, can I ask just a question about linear models in general? So, without a whole lot of experience in the realm, is it safe to say that a linear model can apply regardless of the data set, the industry, the age of the data? Like, linear models will always apply. There just may always be a better alternative. Is that safe to say, or would you kind of maybe jump past a linear model and choose a different kind of model because you're in a certain industry, or you have certain data, or you need a certain answer?
Always is a scary word, but
Yeah, I was gonna say the answer to this would be it depends.
Right. Linear models are often a way to describe things. They won't always work great, and it certainly often won't be the best, but a lot of people, like I think in some of Julia Sogi's modeling videos, she'll still do a linear model as the first thing, just to kind of get a feel for, which variables matter. Is there a here? Do I see anything with a linear model? And then we can start really diving in and trying to figure out which features, how to make the, this linear model says this feature doesn't, says bedrooms doesn't matter. That doesn't make sense. So what am I doing wrong? That kind of thing. So I think even now with, there are pretty advanced modeling techniques.
One of the reasons that linear models are so persistent is, I mean, if you think you have any old curve, like even in multi-dimensions, over a small enough region of your space, it'll look like a line, unless it's really pathological and has kinks in it. So linear models, like, it's almost safe to say, but always is a scary word. But like, if you narrow the range of your data and your domain, like if you zoom in enough on it, then then any complicated model you have will start to look like a linear model.
Yeah.
Yeah.
I guess the other thing is that linear models are so easy to interpret. Like, they're the easiest to interpret. It's this variable has this much impact. Okay, like I can understand exactly what that means. And so that's where they're still like, if a linear model works for your data, it's really, that's great, because then you can start saying, okay, if I want to have a higher housing price, I look at which number has the biggest impact. That's what I have to increase. Or, if I want to find a cheaper house, I can just lower that number. But again, they're not always, the best fit. It's just an easy fit, or an easy to understand fit.
So recognizing that always is a scary word, it's a good place. Linear models are generally a good place to start, at least.
I think,
definitely.
they're a good thing to include in the toolkit. Now, there will be cases where you're like, yeah, a linear model's not going to do anything here. If I am trying to predict the sentiment of a piece of text, like feeding that into a linear model is difficult.
With text, yeah, of course, with text, obviously linear regression doesn't sort of work well. But I think I do want to emphasize that the concept of simplicity in your models, I think that is something that makes me say, I'm leaning towards Ryan. What Ryan is saying is, we should, at least this should always be the start to begin with, because like John, you were mentioning, so you learn a lot about your data, about your model, and then you can approach towards moving towards complex model. And even then there might be scenarios, or there might be times that when you would actually make complicated models, but still your error rate would be much lesser with the linear model. So that, I mean, drives to the point that even if you try certain complicated models, it'll still be linear, can still end up being easier yet more accurate model.
Cool.
Thank you.
Yeah, thank you, Morgan.
Yeah, thanks, Morgan.
Very welcome. I'm happy to present the next part to the continuation of chapter 4, or happy to pass it on whenever you guys want me to.
Let's talk in the channel, but yeah, if anyone would like a shot at presenting, it is a great way to dig into the material, and we can get Morgan's stuff that is done up onto the repo, so you can just continue from there. Andy says that he's able to present if you would like a break, and I think that's great. We don't have that many chapters, so splitting up chapters is good for everyone to have a chance. So we'll assume that Andy's going to present in 3 weeks. We're going to skip 2 weeks, and then we go. All right. Very cool. And yeah, thank you very much. Bye.
Thanks, everyone.